Hi all, today I'm going to be giving a little presentation on the dual form and we're a little strapped for time, so I'm going to jump straight into it. So before I get started, I'm just going to give a little recap of how support vector machines, because that is primarily what we apply the dual form for. So basically we have hard margin and soft margin SVMs. And in both cases, we're doing an optimization problem. So for hard margin, we're minimizing theta squared over 2, subject to this constraint right here. So subject to, it's got to stay outside the margins. Theta point's got to be outside the margins. And soft margin, we're going to be minimizing theta squared over 2 again. But we're going to have slack variables. These slack variables, which we're going to multiply by some constant, which some hyperparameter. And then we are going to minimize this subject to these constraints here that are underlined, and slack variables have to be greater than or equal to 0. And so the dual form is just another way of representing this, which has some advantages, which I'll get into at the end of this video. So I'm going to start by explaining some of the concepts and then jump into an example, and hopefully that'll make everything clear. So first we have the Lagrangian, and basically for the Lagrangian, we are minimizing a function subject to some constraints, which have to be less than or equal to 0. And the Lagrangian is the sum of this function and these things called Lagrange multipliers multiplied by each constraint, where the Lagrange multipliers are greater than or equal to 0. And so the primal formulation is basically where we want to maximize the Lagrangian with respect to these dual variables, or Lagrange multipliers, which I'm going to refer to as dual variables from now on. And then we want to minimize with respect to W. And so just to explain what this means, so for example, like given an arbitrary W here, we want to maximize this inside function with respect to the dual variables. And then so that's basically what's going on the inside. And then for each arbitrary W, we're going to maximize the inside, and then overall we're going to try and minimize like each of those results. And it'll make more sense as we go on. In dual form, we basically just swap the order, swap the min-max, and this works when certain conditions are met, which I won't go into too much. Basically, like if the objective function is quadratic convex, and think about this visually, if the objective function looks like this, then we can, it's quadratic convex, we can find a minimum here. So yeah, the example explaining how this works, we're going to do this for hard margin SVMs. So we're going to start with our optimization problem, and you can see we can turn this into Lagrangian. This is our f of w here, and then this we're going to turn into our h of w by just doing 0 is greater or equal to 1 minus y of I times theta times x of I plus b. So we're going to plug this into the primal form that I showed earlier, and this is what we get. And then we swap the order of min-max to get max-min, and all the time subject to dual variables being greater than or equal to 0. And then now we want to evaluate this. And the way we can evaluate this is, or the way that we can simplify this is we want to minimize this function with respect to theta and b, right? So we can take the derivative with respect to theta and b, two partial derivatives, and set those equal to 0, because at the minimum, as I drew before, it's going to be 0, and we're assuming that the objective function is convex, quadratic, so this should hold true. So yeah, when we do that, we have 0 is equal to this derivative, and I won't go too much into the math, just so we can get through all the content. But yeah, eventually you get this optimal theta when the dual form is, when it's minimized with respect to theta and b, is going to be this sum here. And then when we minimize with respect to b, we get this property, this sum is equal to 0. And then we just plug this all in to our original form, and we get the dual form here. And I won't go too much into the math, but basically we're just substituting theta star here for theta. And then whenever you encounter variables such as alpha yi, we're just gonna set that equal to 0. So yeah, a couple takeaways. First thing is going back to the primal form, you can see how given this constraint here, if first of all, if the constraint is violated, so if this here is greater than, if this here is greater than 1, then this whole function will blow up to infinity. So that's why the constraints aren't going to be violated. If it's not violated, then we have either this is equal to 0, which means that here this term is equal to 1, and we have a support vector, and we'll have the dual variable is actually greater than 0, or this here is going to be greater than 1, and it's not a support vector. And it's kind of interesting to see that dual variable is going to be equal to 0, which means it's not factored into calculating our optimal theta, which we found here, right? Because we need dual variables to calculate that. That's just kind of interesting. But overall, like, the reason that we do this is because the dual form saves compute time. We only have to keep track of the inner products of the feature vectors. So if you have very high dimensional feature vectors, it's going to be more convenient to just keep track of these n squared inner products as opposed to all the feature vectors, which is d times n, if we have d dimensions and n feature vectors. Yeah, thank you.